Testing sound. Looks good. Okay. So, the last couple of days we've been kind of working our way into chemistry. Nothing that's, I don't know. You guys had learned a lot of this stuff before. Maybe not every little detail, but like, had you heard of some of those models of the atom before? That's something to come up. You guys had heard about like how to classify matter as compounds versus elements. Okay. Like, in theory, it should be reviewed from Science 9. But if not, I mean, I'm going to teach it again, obviously. Today we're going to focus on knowing how your periodic table works. And when I teach chemistry, I like to relate this to when my daughter is learning to read. Okay? I'll use my kids all the time as my analogies. My Kinsey Ann, she's in grade 1, she's 6, and it has been so cool for the last 2 years of my life to see her learn how to read. Because she's to the point now where if you give her kind of a small book that has, words that are probably no more than 2 syllables, maybe 6 letters total, she can actually read it, which is so cool. Because like 2 years ago, she couldn't. So if you have little brothers or sisters, or you can kind of think of what it would be like at that stage, what's the first thing that I did as a parent to try to help her learn how to read? What should I teach her first? Yeah, literally the letters of the alphabet, right? My 4-year-old is actually going through the same process right now. In order to help her learn her letters, the first thing she's actually learning is how to spell her name, right? Cameron. So she knows a K, because a K is the first letter in Cameron, right? And we've actually bought some flashcards for her to learn how to do just her basic letters. Well, if learning how to read is similar to learning chemistry, maybe you can kind of see where I'm going here. The analogy between that is that if you're going to learn chemistry, you have to learn the basic building blocks of putting words together. And in chemistry, that is the periodic table. That's our elements. Does that make sense? Now, eventually, you're going to want to put more than one letter together. Like, for example, one of the first words that Kinsey learned, I remember, was the word sat. Combine them together. Well, what happens when you combine letters together into words? What's the analogy for that in chemistry? What happens when you combine elements together? What does that mean? What's the word for more than one element put together? Begins with a C. It's a compound. Does that make sense? Elements, basic building blocks of life. Put them together, you have a compound. A great example of a compound would be something like this. CO2. C stands for carbon, if you weren't aware. And oxygen stands, well, O stands for oxygen, right? Put that together, now you have a compound. So, like if I just had H by itself, I could say that's an element. And if I were to put CO2 together, that's a compound. That's like a word. And eventually, sorry, bear with me. It's very soft, isn't it? Hello, this is Chris. Hey. Okay. Cool. Okay. 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 Send him up. We've only got half an hour left, but yeah, totally. Okay, cool. Sorry, guys. Okay, anyways, the analogy I want to finish off with then is eventually after we finish working with our compounds, when Kinsey learns how to say a word like, say, sat, then she learns how to put multiple words together. In reading, we call that a sentence. We're eventually going to get to that, where we need to then be able to write chemical equations. Something like this, where you have something here plus something here, and then we put an arrow, and it turns into this. That would eventually be a sentence. We call it a chemical reaction. Okay. So we're really at the basic building blocks right here. I need you guys to understand your letters. And hopefully this comes back to what I started the class with. That's why I want to give you a quiz on it on Wednesday. Because if you're really struggling on how to just know your letters, well, then is it fair for me to move on until we make those corrections? No, we have to fix that. So let's start off by talking a bit about our elements. If you guys have your notes in front of you, that periodic table is the top slide. There's also one back here. I'll flip back to them, but hopefully you've seen a periodic table at some point in your life before. Okay. If not, this is kind of the basics of it. I should talk a bit about its structure. It's a table, but it's not like a grid that's exactly perfect. There's actually a couple of holes in the table. There's a big gap right here, and like there's only one sitting here and one sitting here. There's a bit of a gap there. Okay. I'm going to explain some reasons for that later. What I need you guys to know is that there's about 100 and, what are they up to now? 117 or 16 or 18 elements that we've discovered, but some of them are like synthetic, where they only last for a little while, and they're only created if like a person like develops them in a lab and tries to like create them somehow. So we've discovered almost all, well, I think we've discovered all of the naturally occurring ones we're ever going to find. And then this number right here is kind of dependent on where in history we are. There might be another one discovered a little bit later. And those are the ones that are usually kind of down here in the bottom corners there. I need to ask a question. Do you guys know how to tell the difference between a naturally occurring one and a synthetic one? Has anybody ever been told that? Okay. Does anybody have their data sheets that I would have passed out a while back that had like a periodic table and formulas and stuff in there? You guys know what I'm talking about there? Should have passed it out on like the first day of school or second day of school. Because this is actually an important thing. I need you guys to know the difference between how to find the synthetic ones versus the naturally occurring ones. So grab your periodic table if you have it nearby. I'm going to see that I can find a good one on here. Yeah, I'm going to flip to the slide here, only just so I can reference the periodic table. So it should say Science 10 Data Sheets 2018. If you don't have one, can you let me know later and I'll find you one? And then flip to the first inside page of the periodic table. It should look more or less like this one. Okay. Can I blur one real quick? Can I still real quick just to make sure I'm looking at the same one? Okay, it puts it in the top left corner, the top right corner. Okay, if you have your periodic table nearby, they all come in like little squares. And I'll do one as an example, like say hydrogen. Hey, come on in, just take a seat here. I would put H for hydrogen, and then I believe below it they write out the word hydrogen, hydrogen. Okay. Up in the top corner up here is something I want to refer to. There is a number up in this corner here. For hydrogen, it should probably be 1.01. Can you guys find that number there? Okay, that refers to its atomic weight, and we will work with that later. I don't need you to utilize the number yet, okay? But I need you to look at that number there for hydrogen, and then I want you guys to find technetium, which is, I think it's, oh goodness, is it right about there? It's number 43, I think. Try to find the one, like there's a 1 up in the corner. Try to find number 43. Is that technetium? Let's see yours. I haven't used it in a while. 43. Oh, I'm way off. It's supposed to be more over here. Here we go. That's where it is. It's like TC. It's technetium. Okay. And I want you guys to look at that number that's up in the corner on technetium. What's different about it? Two things. One, it's in brackets. And two, it does not have decimal places. It's a whole number. Okay. Now, I will get to that a little bit later if I can as to why those things exist. But can I just tell you for now, if it has brackets around it and it's one of those whole numbers, that makes it synthetic. Sound good? So that's how you know the difference. What's that? Which means that it's not like naturally found on Earth. It means I can't go mine technetium like I can. Like I could go and look for gold and find it in the ground. Does that make sense? But like to find technetium, it's probably the result of a chemist making it in a lab. And one of the reasons why, well, I'll say this now, one of the reasons why it has that whole number there is that its mass cannot be determined accurately because it probably only lasts for a while before it radioactively decays into something else. And so it has a very short lifespan before it actually transforms through a nuclear reaction. It's actually, they're very rare. Does that make sense at all? So that's actually why it has a whole number ratio, because we can't actually determine its mass. Anyways, if I can go back here to the elements bit here, and that's how you know the difference. Okay. Naturally occurring ones, when you look in that box that it refers to, this number up here in the corner, if it has brackets and a whole number, that makes it synthetic. Which just means that it's not naturally occurring, that's all. We can create it somehow, but it probably only lasts for, you know, a few minutes, maybe in a few seconds. Because an element is anything that's like the basic building block of our world that's based on how many protons it has. Does that make sense? Like an element doesn't necessarily have to be like found naturally. Does that make sense? Because you could actually still have it based in a compound as well. Okay, more about the periodic table. We classify the periodic table in many different ways. One of the ways we do it is based on metals and non-metals. So if you guys can find your periodic table, there is a little staircase line over here, maybe you're familiar with. And it helps separate what are known as the metals and the non-metals. Yeah, it's aluminum and boron and carbon and antimony and some of the other ones there. There's this line right here. Everything on this right here, this side over here, is known as a metal. Now, I need to make sure I'm clear about something. Metal does not mean solid. Most of the time, I find that students think that metal means it's like hard, solid, but that's not actually true. Okay. For example, there is actually an exception somewhere in the periodic table right about here. It is Hg for mercury. And I don't know whether it changes the color on yours. Can you guys see how Hg for mercury is like a dark black there? It's a liquid. Most metals are solid, but that is not 100% the case. And it actually works in reverse of that as well. Over here in the non-metal section is one of them, which is I for iodide. And iodide is actually a solid. So you don't have to be a metal to be solid and vice versa. But that being said, it's almost straight across the board. If you're solid, you're probably a metal. And here are some properties that almost all the metals have. And we're going to actually test these tomorrow in our brief activity. They are things like they're strong, they're durable. Does anybody know what this word here means? It's malleability. Anyone ever heard that word before? Yeah, you can shape it. Yeah, you can shape it into like a sheet of metal would be a good example. Like you can like say hit it with a hammer, and it wouldn't just break into a million pieces. Does that make sense? That's malleable. Okay. The other one that students sometimes don't know is this one over here. It's called ductility. Anybody know what ductility means? Go ahead. I think you can probably do some similarities, but I actually have that on here as well, like about conducting electricity. But what you're describing actually is like a similar idea to it. The reason why electricity would flow through it is because you can make it into a wire. That's the key to ductility. If you can make strings of it and like braid it and coil it into a wire, that's ductility. Okay. Not everything has the ability to do that, but most metals do. Does that make sense? So malleability, can you make a sheet of it and like mold it and bend it? And if you hit it with a hammer, would it break it or would it just cause it to like mold? Ductility, can you make a wire out of it? Okay. Hardness is similar to strength, but hardness, there's actually a scale for this. One of the strongest, like I shouldn't say strongest, I use the right word here. One of the hardest things we know of in terms of things would be diamonds. And really the way you figure out how hard something is based on how it scratches something else. A diamond can scratch pretty much anything. Does that make sense? Because it's one of the hardest things we know of. Okay. So it's very similar to strong. The last two you guys can read as well, good conductors of heat and electricity. So those are our metals. The opposite of our metals are our non-metals, and those are found on the other side of the periodic table, and they have all the opposite properties. And then the last thing you guys need to know is the metalloids. These are the ones that if you see the periodic table right here, they're the ones that are kind of in here. It's all of the ones on the staircase, except for there's like one right here that doesn't fit. And I believe that one's aluminum. I think this guy right here is aluminum. Otherwise, if it touches the staircase, it's a metalloid. And they're kind of like the in-between ones, where they sometimes act like metals, they sometimes act like non-metals. They're kind of like they're in both categories, hence the word metalloid. So you should, I guess, write these ones down or circle them. But I bet you, like, here's my general way of knowing it. If it touches the staircase line, it's a metalloid, except aluminum. I just happen to know that because I know aluminum's a metal. Does that work? All right, cool. More about the periodic table. Based on the way we categorize it, there are 18 groups, and these are where it goes up and down as like a column. And basically, these things have similar properties. When Mendeleev was developing his periodic table, this was one of the first things he did. Is he grouped things together that had similar characteristics. Again, we're going to talk about properties tomorrow in activity. Right? So there's a few that have special names. Everything in group 1 is known as an alkali metal. So if you can kind of imagine the periodic table, I'm just going to kind of draw just a really brief one right here. Let's see, we'll do hydrogen there. Kind of looks something like this. All right. Group 1 would be this first group right here. These guys are known as the alkali metals. And I do need you to know this. By the way, I should let you know, you guys may use on my assessments your periodic table booklet here and anything you write on it. That's always my rule. So if you want to just write in your periodic table that those are the alkali metals, you may have that on my test. Okay, that's my rule. A really smart guy once had a quote. I use quotes all the time. He said, never memorize things you can look up in books. That was Einstein. Figure if it's good enough for Einstein, it's good enough for us. So if you want to write it in, go ahead. So group 1, alkali metals. The second group also has a name. These are known as the So this is the group. The first one has like hydrogen and then sodium and lithium. I think I have those backwards. This is the group that'll have magnesium and calcium in it. On the other side of the table, a couple of them have special names as well. Going backwards from the other side, group 17 is known as the halogens. This is the one that includes things like fluorine, chlorine, bromine, and iodide. They're halogens. And then the last group, number 18, is known as the noble gases. And there's actually a story behind why we call it the noble gases. Everything in this last group right here is non-reactive. They actually do not combine in elements. It would be like, and this doesn't work exactly, but you know how I talked about letters and words? It'd be like the letter Q. You know how the letter Q does not fit nicely into most words? Because it has to follow a U? Okay. It doesn't work exactly like that, but basically we never find things like argon or krypton or xenon in compounds. They never join with anybody. And it actually has to do with the fact that they're actually full up of electrons. So there's a name for that. We call them noble gases. And the reason why they're called nobles is that like way back 200-300 years ago, the nobles were like hoity-toity or aristocracy. They wouldn't hang out with anybody else. They'd have their noses, they weren't going to look down at the peasants, if that makes sense. And that's kind of like what these guys are right here. They don't hang out with anybody else. They don't react, so that's why they call them noble. But the other word you might hear is the word inert. And inert basically also means non-reactive. So that's up and down. Side to side is known as a period. And this is really important here. I need you guys to know that there are actually only 7 periods in the periodic table. Some people look at this periodic table and they say, hi, guys, Chris, I can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, and they think there's 9 rows. That's not how it works. To save space, right here, these two guys, really, all of this stuff should be like shoved right in here. And this periodic table should actually be like way longer across. But if we did that, then like you'd never fit it onto like a sheet of paper. So that's a space-saving room. So you guys might see on whatever periodic table that these two ones right here, the one in like group 3, it actually, this is lanthium, which goes down here, and this is the actinide series down here at the bottom. So there's actually only 7 rows. You guys know that? A couple of you were nodding as I said that. So now I want to talk a bit about atoms, okay? Because really, these things, these elements, they're based on the concept of an atom again. So they are defined very specifically by this concept right here. How many protons are in their nucleus? Okay. That is what that number in the top corner means. When I give you one of these squares here, where I give you, say, sodium, Na, which I believe is number 11, the 11 here refers to how many protons it has. It is defined, its identity is defined by its protons. If you have 11 protons, you're sodium. If you have 12 protons, now you're not sodium anymore. I have a really dumb analogy for this one, so you may think this one's stupid, but I'll go through it anyways. You guys ever watch the TV show The Smurfs? You guys know the Smurfs? How do the Smurfs get their names? Well, their identity of their like defining characteristic gives them their name, right? Grumpy Smurf is called Grumpy because he's grumpy, right? Okay, this is dumb, not dumb analogy. But the reason why we call it sodium then is based on its identity, based on how many protons it has. That's what determines what we call it. Okay, I know the names are based on like maybe like historical scientists, but like we define who something is by its proton number, just like the Smurfs are defined by their, I don't know, their characteristics. You guys, your names came from your parents, I guess, right? So that's the most important thing I need you guys to know. Identify something based on its proton number. Change its proton number, and it is now somebody different entirely. Sometimes we're going to draw things in like a diagram like this. If you're wondering, this diagram or the one on the previous page, this is known as a Bohr diagram. And I want to revisit what we talked about last day. Bohr had this crazy idea, which we actually believe to be true, which is that electrons don't actually orbit and go like in circles like the Earth goes around the sun. He believed they live in like energy levels, and that they literally will teleport, for lack of a better word, from like this level to this one. You would never ever find an electron sitting right there. That's not how it works. If this electron, for whatever reason, needs to move and go from here to like that, like little orbit shell, it would just instantly go there. You would never find it in between, which is like crazy cool stuff if you want to talk physics with me. So anyways, the reason why we use these Bohr levels is to try to help describe atoms and ions and how many electrons and protons there are. So we've already talked about protons. Right here I put the letter O. O is oxygen. Oxygen is defined by how many protons it has. So oxygen has to have 8 protons. That's just, if you have 8 protons, you're called an oxygen. But here's the thing you guys may not know, is that if we're talking about an atom, atoms are neutral, and so your protons equals electrons. Which means if you have 8 protons, you should also have 8 electrons. And you can actually count up these electrons here. There are 1, 2, 3, 4, 5, 6, 7, 8. So in this guy right here, there were 8 protons. I'll go P plus for that. And there were 8 electrons. These should be the same as each other. Magnesium, similar. Magnesium is also defined by its protons. Magnesium has to have 12 protons. That's what makes it magnesium. But you'll notice that it also has 12 electrons if you count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. One day, I'll probably be able to explain to you why they always come in pairs. It's a term called quantum entanglement. Again, crazy cool stuff. We'll get to that. We're not there yet. But they always come in groups of 2. Other thing I need you guys to know, though, is that these little like rings right here, we call them orbitals. There's actually a pattern to it. The first ring always gets 2 electrons. And that is actually based on how this first row right here has 1, 2 things in the first row. Ooh, why am I still drawing here? The second row always has 8 electrons, like 1, 2, 3, 4, 5, 6, 7, 8 in the second like ring, kind of like a tree or an onion has rings. And that is based on the fact that there are 1, 2, 3, 4, 5, 6, 7, 8 in the next row. So there's actually a pattern to this. Each one of these like rings that you would see in a Bohr diagram actually refers to how many like slots there are in each row on the table. Yeah. No, they don't necessarily, but there's actually some evidence that they can actually communicate with each other if you move them long distances away. If you take the pair of electrons and you move one of them really, really, really far away, what we've discovered is electrons are always spinning. They're either spinning clockwise or they're spinning counterclockwise. And we actually don't know which way they're spinning until we look at them. 2 electrons really, really, really far away, and all of a sudden I look at this one over here and see which way it's spinning. The other one will automatically spin the other way. And like, it's weird. It's almost like they somehow know each other. Einstein called it spooky action at a distance. So anyways, I'm getting way ahead of myself because that's physics 30. But yeah, they don't have to go in groups of 2. Yeah.
Does it like change the properties depending on the interaction?
Not that I'm aware of. No, because it's still an electron. Yeah. Anyways, I got to move on here because I've got 10 minutes left. When it comes to these electrons, then, when we count up how many electrons there are, the outermost energy level is the really, really key part of it, because it tells us how it can form an ion. Okay? The words I need you guys to know are that atoms are neutral. Atoms always have equal protons to equal electrons. But ions, you can change the number of electrons. Now, you can't change the number of protons. If you change someone's protons, they become somebody differently entirely. So I can't add more protons to oxygen. But you know what I can do? I can change its electrons. And the reason I can change the electrons is because they're kind of in these outer areas here. So like, you can take this electron and move it. That is possible. I mean, literally, the movement of electrons, we have a name for that. It's electricity. Right? When electrons are moving in a circuit, it's electricity. So you can move the electrons, but these protons right here, they are stuck. They're fixed. Until you get to physics 30, we talk about nuclear equations. It's one of the tough things about chemistry is I'm kind of like, I want to explain things to you as much as I can, but like sometimes I have to like build you up to it, if that makes sense. So, anyways, the point I want to make is that the outside-most ring is what really matters. The outside ring has valence electrons. So if I were to ask you guys to look at oxygen, how many valence electrons does oxygen have? And so you'd look at the outermost ring and you'd say, well, there's 1, 2, 3, 4, 5, 6. Perfect. Or if I asked you how many valence electrons magnesium has, you look at the outside ring, and you'd see that it has 2, so you'd say it has 2 valence electrons. Those are the electrons that we can kind of mess around with. We can either add more electrons to them, or we can actually get rid of them. Okay. if you have, say, a lot of electrons, full energy level, how many electrons can you fit in the second level? Well, you can hold 8. And so if you can hold 8 electrons in this energy level, this guy right here really needs 2 electrons. Because he's at 6, but the full capacity is 8. If he can get more electrons, no longer are electrons and protons the same. Now it would be called an ion. And that's what I have on this slide right here. Where do I have ions? Oh, maybe I don't have it on this slide here. Here it is. Can I hop to this one right here? Ions is when you don't have the same number of protons and electrons. Ions either get or lose electrons. And maybe the best way of me doing this is just to do an example here. Let's do sodium. What number on the periodic table is sodium? Okay, so that means sodium better have 11 protons in its nucleus. So often we just draw that around a circle. Then we draw our first ring. How many electrons, capacity-wise, fits in the first ring? 2. Okay, so I'm just going to put 2 of them there, and we often put them in a pair. I like to write E negative for electrons. That's our first ring. Then in our second ring, what's the capacity of the second ring? 8. So 1, 2, 3, 4, 5, 6, and 7, 8. How many electrons have I used total? 10. Right? 2 plus 8 gives 10. Well, I need one more electron because an atom would have equal numbers. Right? So if I draw, that better be equal to 11 electrons in an atom. So I need one more electron. And here's the thing though, that one electron is not near full on the next energy level because the next energy level needs 8 and there's 1 out of 8. Like, is 1 out of 8 even, it's not even half, it's not even close to halfway there. You get what I'm saying? And so what ions do is ions get rid of electrons and they say, let's just ditch that guy right there. You go somewhere else. Well, now it's no longer an equal ratio. Now we still have 11 protons, but now there are 10 electrons in this ion because we got rid of that extra electron. Who wins between protons and electrons? Who is there more of? There's one extra proton. And so sometimes we see in the little corner there a little charge, like a plus, or a 2 plus, or a 3 minus. And that indicates to us whether or not there's more electrons or more protons. And so if there's a plus in the corner, that must mean that there's one extra positive. We don't write the 1, by the way. You could write the 1, but we don't usually write the 1. So the 1 plus implies there's one extra proton. This is really important. Did it get the extra proton because it added an extra proton? You can't change your protons, because otherwise you're no longer Grumpy Smurf, now you're Smiley Smurf. Right? Your protons is fixed. But what you can do is change your electrons. Now, electrons are negative, so if you want to make something positive, just get rid of one of your negatives. And that's where this little charge in the corner comes from. Yeah. So it doesn't change the element. It's still an element of sodium, but now it's no longer an atom. It's now an ion. That's the terminology we use. The key thing about ions is the positive ions and negative ions can suck together and form compounds. And that's what we're going to get to over time. Okay. Here's another kind of pictorial diagram of what I've got there. What you guys might notice here is that everybody in this last column, group 18, it's full. This ring right here is full of its 2 electrons. It's done. It doesn't want to gain or lose electrons. This guy right here has got his 8 in his last ring. It doesn't need to gain or lose any electrons because 8 is like at capacity. And that's why these ones in group 18 are all considered noble gases. But if you guys look at your periodic table, you might notice some trends. Everybody in group 1, does it say the charges on your table? Yeah, it does. Everybody in group 1 is +1, or 1 plus, whichever way they do it. And the reason why is that they all have 1 electron in their last energy level. If you can ditch that 1 electron, well, you have 1 less negative, it must make you positive. Everybody in this column is like +2. Everybody in the next column is usually +3. Now, that does break down, by the way. That doesn't work all the way on the table, but it's a very good rule. And the same thing kind of goes on the other side of the table. I don't know whether it says it there. Yeah, it does. All of these guys right here are -1s. And the reason why is that their outermost energy level, this energy level has room for 8 electrons. And there's 1, 2, 3, 4, 5, 6, 7. You know what this guy really needs? is an 8th electron. Where might it get that electron from? This guy over here. This guy doesn't want an electron, and these guys over here do want electrons. And that's why you get compounds like NaCl, salt. Because Na wants to become positive by losing an electron. And chlorine is 1- because it wants to gain an electron. And this is what we're going to focus on after our quiz, is the idea of when you put these things together, that's how compounds get named. I am rapidly running out of time, and so I'd like to finish with my last slide, and then tomorrow before we do the activity, I will do all of like the in-between stuff I missed, okay? So can you guys find, sorry I'm skipping some, can you guys find this slide right here? Second last slide. I want to try a quick activity to see whether we've kind of got the idea of how this looks, okay? And then tomorrow we'll do like our lab kind of thing, and then Wednesday we're going to do a quiz on this. Okay? So I will come back to what I skipped. It's just I've got like 2 minutes left. Let's say I told you that something had 17 protons. Do we know what its name is? Yeah, because 17 guarantees we know who it is. Who's number 17 on the table? Okay, so that's what I want to do in this task, is we're going to call this a chlorine. Okay. Now, the next thing I want to do is focus on something called an isotope. Okay, the isotope tells you how heavy something is. Last class, what was that, Friday? I think I talked briefly about neutrons. The way it works is that if you add your protons and your neutrons together, it tells you what isotope it is. Neutrons don't add any mass or don't add any charge or change. It just makes them heavier. So if you want to figure out how heavy this molecule is, it's going to be 37. And the reason why I came up with 37 is because 20 plus 17 adds up to 37. Protons and neutrons are found in the nucleus, and they actually weigh a considerable amount. Electrons are so light that you would need over 1,000 electrons to weigh 1 proton. So we don't ever count electrons. The last thing we have to figure out is whether this is an atom or an ion. Is it an atom or an ion? Well, look at protons versus electrons. Is it the same as each other or not? It's not. So that makes it an ion. But I need to tell you what charge it has. It's an ion of -1. And the reason why it's -1 is because there's more electrons than protons. Can I try a couple more here? Can you guys just stay with me until they call us away? I know some of you are starting to pack up here. I will finish this. We'll start with this next day. Let's try a couple more until I run out of time. 10 protons. I should now know who it is. No, never mind. Okay, we'll start with this next day, okay?
Students and teachers at this time, if you could please make your way